Hello.
Yes, sir.
Am I audible?
Sorry? Yeah, you are audible. sir.
Hello,
Yes, sir.
is my voice is clear?
Yes.
Okay, okay. So,
Actually, I am studying regarding one.
your voice is not clear actually. Can you speak again?
Yeah. Can you hear me now?
Yes, yes.
There is some issue with my microphone. Yeah. Actually, my question is regarding the question number 10 in the assignment of week 5.
Question number 10 in
Okay. Assignment of week 5.
week 5.
Yeah, yeah.
Okay. So, what is the question? Can you just share in the typing?
Yeah. Just give me one. Just give me 1 second.
Sorry?
I'm just copying. I'm just copying the question. Just give me
Okay,
a
okay.
second.
Question number 10.
Yeah, yeah. Not in this that you have written, like in the original assignment.
Original
Previous
assignment. Okay, okay. I do not have access of original assignment.
Okay, just give me 2 seconds.
So until I have explaining, you just type the question and then I will see the question. Okay.
Yes, yes. Just give me 2 seconds.
So-
I'll just copy.
In this week, the most of the time is given for the metamaterials. So first question is, in this week, the mostly discussed part is metamaterials, right?
Yes, yes.
In 6th week. So in that way, the uh, topic was introduction to metamaterial. And then second was metamaterials at gigahertz. gigahertz and terahertz frequencies. And the third one was negative index material at optical frequency. Negative index material at optical frequency. And then was plasmonic metasurfaces. And dielectric metasurfaces. And what is the last date to submit this assignment number 5? Sadhu Khan, can you tell the last date of submission of this?
Just give me 1 second. I think the date has gone. Okay. And the answers have already been given.
Okay.
Because 28th August. Okay. Actually, the issue is like I obtained the answer of 500. Okay.
500.
But yeah.
Okay.
But the solution that has been given in the solution, it is 750. So I couldn't
750.
understand like.
Or your answer is 50.
500.
500, sorry. So what is the question? I will just repeat first. The question was, a periodic diffraction grating is fabricated on glass. So refractive index of glass is given 1.5. Substrate with 100 slits and a periodicity 2 micrometer. Okay, this is periodicity. Periodicity is 2 micrometer. An electromagnetic wave is incident normally on the grating from the air, resulting in a second order maxima subtending at an angle of plus minus 30 with respect to the normal. Okay, what is the wavelength in micron of the incident? Right, this is the question. This was the question, right?
It is what is the wavelength in nanometer?
Sorry?
The question is, what is the wavelength in nanometer of the incident wave?
Resulting in the second order. So you are asking what is the origin?
Yeah, what could be the wavelength? Because when I solved it, okay, I got an answer of 500 nanometers.
Okay.
So I compared some of my friends, they also got the similar answer. But the solution, the accepted answer that has been given here, it is 760 nanometers. Okay.
Okay.
So, that is the issue.
So I think I solved this question in the tutorial 5, if I remember right. This was one question. There was one question such that. Yes, I solved it.
It was a 10 question, sir?
It will come around 625, right? No, not 625. So what is the condition of maxima and minima in grating system?
Yeah.
If this is our screen and these are some slits, and this will be our center of line and its central maxima, and they are asking for second order maxima, right? So m will be 2.
Yes.
And here m equal to 1 and this is m equal to 0. So
yes.
Condition was not 2D. d sine theta is equal to
m lambda.
m lambda, right? So m is
Yes,
the
sir.
order of fringe.
Yeah.
Okay, so
Yes.
m is the order of fringe. Then d is given our periodicity, right? D is the periodicity,
Yes, sir.
and theta is the this one. This theta 2, this is theta 1. Okay,
Yes, sir.
so for m equal to 2, this theta is equal to 2, then d is 2 micron multiply by sine 30,
Yes, sir.
right? It will
Yes,
be
sir.
either 30 or if we take this, then it will be minus 30, right?
Minus 30. Yeah.
Equal to m is equal to 2 and lambda
Yeah.
we have to find out, right?
Yes, sir.
Or lambda is given.
Mm-hmm.
Right, so once again, so what is the wavelength in nanometer in incident wave?
Yeah,
Okay.
I have used the same relation and I got the answer of 500 nanometers.
So lambda is equal to 2 sine theta upon 2 mu, right? 1
Yes, sir.
sine 30. Okay. Here is one a diffraction grating is fabricated on the glass. So this D is not the actual D. This will be Dn, I think. Okay, because glass refractive index is also there. If it I put this one, then this will be 500 multiply by 1.5, right? So this will be 75 nanometer. Got it? So this periodicity is the path difference between this thing with which the light will see. A light will always see n into d, this path length light always see. Okay, that's why this answer is 750, not 500. For the general condition which we are we put like air is the in air, but it is given on the glass, right? Okay, so little bit played with you with the question. Okay, so the question was the discussion was on the diffraction grating, not diffraction, introduction to the metamaterial. So I hope you have seen, so I just recall some of the important formula and some concept. So what is the metamaterial? So let's we have the coordinate between epsilon and mu. So in this quadrant, mu is greater than 0 and epsilon will also greater than 0. So what the physical significance will be, the light will propagate in such materials which epsilon and mu both are greater than 0. And also if you see, this E vector will be in this direction and K vector will be in this direction. Let's say H vector in this direction, and then the propagation of energy, that is called S vector is equal to E vector cross H vector, right? So this S vector will be also in the direction of K vector in such material. So these are the normal material you can find in the nature. While if you go to the material section, then epsilon can be negative and mu if we take greater than 0. So these are mostly the metal. In the metal you can find, or some doped semiconductor, you can find this uh, epsilon less than 0. Okay, so in this coordinate also this E and K vector will be perpendicular as it always has, and the S vector will be in the decaying region, right?
Yes,
Similarly,
sir.
sorry.
Yeah, okay, sir. Please continue.
So the wave will propagate in a evanescent region. Okay. Similarly, like if we have mu less than 0 and epsilon is greater than 0, so sum of ferrite if you find, so they have such property that mu is less than 0 and epsilon is greater than 0. In such case also the wave propagate in the like evanescent wave. Okay, so in this one also like E vector and this K S will be decaying as the Z increases, and this is exponential relation you can find in the initial of the lectures. But in this coordinate what will happen, the epsilon will also be negative and mu also will be negative. So in nature there is no material such that the property have epsilon less than 0 and mu less than 0. Okay, so this results in the negative index, and this type of material we can fabricate, and like we can say this is not the natural condition, so but man-made material we can made. So these type of material we call metamaterials. Okay, so these are some type of negative index, as already said. So like if you find this relation S is equal to E cross H, and if we have E such that E naught e to the power minus I k dot r minus omega t, this is the plane wave question we consider always for the example. And if we have k cross E in this region, so this comes out around mu omega h vector. Okay, similarly if you find k cross h, so it will come minus epsilon mu E. Okay, so if epsilon or mu anything will be negative here, then this will be positive, right? So if you find here from here h will be k cross E upon mu epsilon. Okay, so this h, if you have mu or epsilon will be negative, then h vector will be negative, right? So if you find E cross h in such case, so this will also equal to S vector, which is 1 by 2 real part of E cross h. So if you find this E cross h, so E you can find, or you can convert anyone, H or E. So I would like to convert H into E, then you will find E cross K cross H upon mu omega. So sorry, this will be E. So it will be around K into E square upon mu epsilon, right? So if you find this S vector, if any one is negative, like mu is negative, epsilon is negative, then the K vector and S vector will be in the opposite direction in this section. So E will be in this direction, K let's say in this direction, and H in this direction. Then propagation of energy will be in the opposite direction. So this is the main property of this metamaterial. The metamaterial, And what to next? So all these type of material is called metamaterials. So in this reason we solve Maxwell equation to see the response of such materials. And also if you compare with the wavelength, so the unit cell will be less than lambda for the metamaterials, and if it will be in comparison of lambda, then we say this is photonic crystal we talk about in previous lectures. And if this A is greater than lambda, then this is normal material, and we can explain from the transition theory. And in this region we always solve the Maxwell equation, and in this region we use guided mode theory. Okay, then sir discussed about like some metamaterials, like if we have one layer, second layer. So like let's say this is epsilon 1, this is epsilon 2. Okay, this is epsilon 1, this is epsilon 2, epsilon 1, epsilon 2, epsilon 1 and epsilon 2, like that. Then the effective index will be like E parallel is equal to epsilon 1 f1 plus epsilon 2 f2, right? And epsilon perpendicular will be epsilon 1 epsilon 2 upon epsilon 1 f1 plus epsilon 1 epsilon 2 f2. Is it right?
Yes, sir.
Okay. So these are some these are formula for effective indices theory. So we cannot consider the whole structure, we can just consider effective index, effective permittivity in parallel direction and perpendicular direction. If we have some metamaterials like such that I have one metamaterial like a disk array. Okay, so let's say this is epsilon 1 and this is epsilon 2, then epsilon parallel and epsilon perpendicular we can calculate according to this formula. Okay, and using this theory you can calculate the transmission and reflection from this type of meta surfaces, and other thing you can solve the Maxwell equation. Okay, so these are some approximation theories just. So for example, if I would take one question from tutorial, so question 1 is for a bulk dielectric material, we have epsilon greater than 0 and mu is also greater than 0. Then the energy flow that is Poynting vector. You know the Poynting vector? And the propagation that is K, R and then dash. So options are in the same direction. Second one in the opposite direction. Third one was orthogonal to each other. and fourth was at the angle of 30 degree. Or equal to minus 30.
In this case, one will be the answer because since it is normal dielectric, so in that case it is so K will be equal.
So this is one type of question it may ask in the exam also. Like it can also be changed, like if epsilon less than 0 and mu is greater than 0, then what will happen? Or the other condition may can someone can give epsilon less than 0 and mu less than 0, then what will be the option of this one for this case?
In that case, K will be in the opposite direction.
Yeah, so this will be this 2 for this condition. So you just solve this question from this figure only. Okay, so
Yes,
that's why I explained this concept again. Similarly, the next question is you can consider a multi-layer structure that is titanium silicon, ti and silicon composite. So the permittivity epsilon of ti will be minus 4 plus 12i, and epsilon of silicon is 15 plus 0.2i. So at the wavelength of 600, then the thickness of each layer is much smaller than incident wavelength. So maybe thickness is around 100 nanometer or something. This is much smaller than 600. Okay, and FTI and FSI are filling factor of titanium and silicon. So let's say FPI is the filling factor for ti and FSI is the fill factor for silicon. Okay, so the question is, this is the journal statement. Let's say FPI question number 2 is equal to 0.6, then what is the epsilon perpendicular parallel?
Okay.
Solve it. 2 minutes you have.
Hello.
Yes, I got it.
The answer is 3.6 plus
Yeah,
7.28.
answer is 3.6 plus 7.28 I, right?
Yeah, yeah.
So similarly, so should I solve it?
There is no need. Actually, just I have made the assumption in the what was done
Yeah.
in the class. Like
So
so I have taken f1 plus f2 equal to 1. So
yeah,
here the
FSI
assumption I
plus
have.
FTI will be 1. So FSI
Yeah,
will be 0.4. So you can
yeah.
easily find
So,
from this.
can you just tell me like why this thing is happening? Like why f1 plus f2 will be equal to 1?
This FSI plus FTI equal to 1, right? Are you
Yeah,
asking this one? Why?
yeah. Why?
Okay. So let's you have stack like that. This is the whole structure. Let's say this is tie. This is SI. This is again tie. This is again SI. This is tie, and this is again SI. And this is SI. Okay. So now what is the periodicity? Is this is the periodicity?
Yes.
Okay. So
Yeah.
if you take one unit cell,
Hmm.
so this is F is the fill factor. Okay. So fill factor is like the filling factor. If you see, have you read about the lattice crystal or something about that?
Yeah. Are you talking about that HCC, BCC, lattice?
Yeah. So in that one you must have find something like filling factor like that.
Yeah. Right.
Right.
But
So
that's the solution, right?
similarly,
Correct.
this
But
is the same thing. This is the fill factor. What
okay.
in the total unit cell, what area is filling with silicon and what area filling with tie.
Okay. Nice.
Okay.
Okay. Thank you.
Hmm. So filling factor is uh, area of SI upon total area. Similarly, area of tie upon total area, and the total area will be silicon का area plus tie का area, like.
Okay. Okay. Sir.
Okay. So similarly, question number 3 is uh, in for the same thing you have to find epsilon perpendicular.
Okay. That should be easy. So this will be a simple multiplication. Like
Sorry,
this will be just simple multiplication. Just
multiplication.
not like epsilon one epsilon two by f1 epsilon two plus f2 epsilon one like this.
Yes. So this is a in the last year this was 3 mark question in an exam or
Okay.
eh?
Okay. So it is very important.
The concept is important and what you learn from this course, that is important. uh, all things are easy if you go step by step.
Yes. So this is just coming some multiplication terms like yes, I have to do some factorization of complex numbers.
Factorization of complex number.
Yeah,
Yes.
yeah, yeah.
Yes.
You just can escape this one. It's very easy.
Sorry.
So you can just escape this one. It's very easy, no? You just wrote down the formula just about this.
Yeah. So the formula is epsilon perpendicular equal to epsilon tie epsilon si upon fsi epsilon tie plus f tie epsilon of si. I think I write wrong in here. Yeah, this is epsilon plus this epsilon point. Okay, so you
Yes,
just put the values and you will find answer is 5.32 plus 20.68 I.
yes.
So the effective permittivity in direction of propagation of the incident wave, that is epsilon perpendicular, for a filling fraction fsi is equal to 1. If we take fsi is equal to 1.0, then what will be the epsilon perpendicular and epsilon parallel?
Okay. Yes, five, 1.0. For the same question, right?
Yeah.
So this is 1.0. Okay. So it's 0. The perpendicular distance.
So you can solve it simply by logic. Like if you do
Yes,
not
sir.
dope you do not give any other material, then we see only silicon. Okay.
Yes,
So
sir.
this epsilon perpendicular will be only epsilon silicon.
Okay. So, sir, why the parallel terms will be gone? Like, it will be
No,
anisotropy.
parallel terms will be there. Uh, Parallel also will be epsilon equal to f si epsilon si, right? And this fraction
Yes,
is
yes,
0,
yes,
so
yes,
this
sir.
will be epsilon ti.
All the diagonal terms will be equal.
Sorry.
Since silicon is like
Yeah, homogeneous,
isotropic,
then it will be the
isotropic.
same epsilon in the all direction. So
Yeah,
whatever
yeah,
he will
yeah.
asking epsilon perpendicular or epsilon parallel, it will be both equal,
Yes,
and it will be equal to epsilon of silicon.
yes.
So question number 5 to question number 7, this is the common data I will give. So consider a two-dimensional periodic metallic, you can consider silver wire array embedded in dielectric medium. The radius of the wire is R equal to 5 micrometer and periodicity is A equal to 40 mm. So this will be like this is the unit cell and this is your, so this is 2R and this is A. Sorry, this is the square, not rectangle. So the electromagnetic wave is incident on the material such that incident wave propagating in the x direction and is polarized along the z direction. Have you understood?
Yes, sir.
Okay. So this will be x direction, this will be the y direction, and light will propagate in from z direction. Okay. So
Okay, sir.
now the question is the effective carrier concentration of the material is, we have to find effective carrier concentration of the material, that is in meter cube, sorry, per meter cube. So that carrier concentration of Ag is given 5.8 into 10 to the power 28 per meter cube.
So 29 into 10 to the power 6 per meter cube.
20
29 into 10 to the power 26 per
26
meter cube. Yeah.
no,
Okay.
maybe some calculation mistake.
Yeah, it is n ag into pi r square by a square.
Sorry,
The formula
n into pi
r square by a square.
by a square, that is the correct formula you are using.
Oh, okay, okay. I made a mistake. I took a 40 micron. Sorry, I made a mistake there. Sorry. Okay, sir, is it 10 to the power 20? 29 into 10 to the power 20?
21 आएगा, 10 to the power 21.
Okay. Yes, sir, it is 2.9 into 10 to the power 21.
2.85 into 10 to the power 21.
Yeah, 2.9 I am getting. So, 8 is the
So I discussed the formula in the lecture. So N effective will be again filling factor multiply by M. So whatever the filling factor, area of whatever we have material upon area of total. So N is multiply by pi r square upon area of a square, right? So this is given 5.8 into 10 to the power 28. This will be pi multiply by r. So r is given 5 micron. So 5 into 10 to the power minus 6 whole square upon a is given 40 into 10 to the power minus 3 whole square. So it will be 5.8 multiply by pi multiply by 5 40 by 40, and it will be 10 to the power minus 6 10 to the power minus 12. So minus 12 plus 6, so it will be minus 6, so it will be 10 to the power 22. Okay.
Yes, sir.
So 5 8s are 5 8s are, you can just multiply it, may come 0.285 into 10 to the power 22. It will be 2.885 into 10 to the power 21.
Yes, sir, I got 2.9.
You got 2.9
into 10 to the power 21.
21. Ah, that is okay. So this was the question number 5. Similarly, question number 6. This is 2-hour class. My questions are very less, I think. I have to increase the number of tutorial questions. So the plasma frequency of the metamaterial is approximately. Next question.
Okay.
It is given M effective equal to 2.1 into 10 to the power minus 25 kg. So very less people are joining. What is the problem? I don't find. Either they left the course or they are not interested.
That I can't comment. Do you know that how many people have registered for the examination?
Not examination. I see the total number of registration around 700.
Okay. Actually, sir, I am just ready to give the exam. So, like in my area from Kolkata, the seats are limited. So that's why I am worried.
So you are from Kolkata?
Yeah, yeah.
Okay. I was been there for 2 years.
For your
Not
MSc?
in Kolkata, but in IIT Kharagpur.
For your MSc?
MTech.
Okay, okay. You are from electrical engineering?
No, I am from physics.
Okay, you have done your MSc then MTech from KGP?
Yes.
Okay, okay. So how was your stay in Kolkata?
It was nice. I like the cheap food from there. Like in price wise, there are very less amount you can eat compared to other cities.
Yes, sir, that is one good thing. Like,
And food quality was also good. If you see,
you are from IIT Madras or IIT Hyderabad?
now I am IT Bombay.
Oh, acha, okay, okay. One of my friend was doing his PhD from there. Uh, just last year he completed his PhD.
Okay, in IT Bombay.
Yeah, yeah. From
So you are
operation research.
what are you doing, like MTech or
I am pursuing PhD.
sorry, pursuing PhD
I am pursuing PhD. Yeah, yeah.
from here?
Jodhpur, Jodhpur, IIT Jodhpur.
Sorry,
IIT Jodhpur.
oh, IT Jodhpur.
Yeah.
Okay. So from electrical department.
No, no, I am from physics.
You are also from physics.
Now, actually, I have a degree of MTech, but due to some reasons like uh, under whom I am doing my PhD, he is from physics. So,
Okay, so you are doing physics, doing PhD in photonics.
yeah, yeah, right.
Okay, my PhD is also going in photonics only.
Okay. You are doing theoretical or experimental?
Both.
Okay, nice, nice. You are working under whom? Like,
Professor Anshuman Kumar.
okay. No, I didn't heard of him. You are doing in physics, right?
Sorry.
Physics department. You are doing from physics department.
Yes.
Okay.
Actually, my topic is on metamaterial only.
Okay.
So you are doing theoretical or experimental?
Mine is theoretical, completely theoretical.
Completely theory. Theory, the simulation or analytical?
Analytical.
Analytical. So you use Python or
Mainly, I do just numerical analysis in MATLAB or
but
Scilab.
numerical analysis in some software, right?
Yeah, yeah, MATLAB or Scilab, whatever you
Oh,
want.
MATLAB. Okay.
The answer for this one is 1.3 into 10 to the 11.
Answer of this one?
Yeah, 1.3 into 10 to the 11.
1.3, no. So plasma frequency will be in hertz. So 1.3 into 10 to power 11 means, sorry, 1 point or 3 point.
1.3 into 10 to the power 11.
So 11 means if you go to 12, then it will be gigahertz, right?
Yeah, 0.13 gigahertz.
No, it will come around 1 gigahertz.
Okay, there may be some numerical
Hmm.
calculation.
Just solve again.
Okay, actually in the class sir has written another formula like 2 pi c square by a square by ln a by r. So will it be okay if I use that formula? Yeah.
Plasma frequency of, because this is metamaterial, this is not the material. Okay, so
Okay.
you cannot choose the exact value, so you have to find the effective index or effective number of, like if material will be continuous, then you can use that formula, because this is for bulk material, right?
Okay. Okay. I got it.
So this is the metamaterial, so it should be pattern, and so there will be some effective uh, charge carrier, not the exact charge carrier which is given. I think that is the difference.
Okay, then AM60 will be 0 R square in
Actually, I am doing this TSF under PMRF things.
yeah, that I can see from
So
your
this is
page.
compulsory for 2 hour. I have to teach.
Okay. Yeah, that I could understand. Like previous year, seemed like you had to just had to sit for 9 p.m. Do you have to do TAs in your TA also, like in your
In my
institute?
institute also, I have done 3 TA,
Okay.
and now in this semester I am doing 5 TA total.
Yeah, these are very hectic.
Yeah,
Office.
because some of instrument I also have TSF, departmental TSF, and then this TSF.
Hmm. Yeah, I think I made some calculation mistake here.
Yeah.
So you just like what would be the answer? Like maybe somewhere I made some mistake,
So
but
the formula is omega p effective square. It will be an effective
oh, there is a square, right? I
E
made
square
mistakenly.
upon epsilon naught m effective star. So n effective I have done 2.85 into 10 to power 21, and E is 1.6 into 10 to power minus 19, and epsilon naught is 8.85 into 10 to power minus 12, and 2.1 into 10 to power minus 25. So it will be 10 to power minus 12 minus this plus 12 plus 25. It is 12, 25 is 37, 38. So this will be minus 1. Minus 1, and this is 10 to power 20, right?
Yes.
And 2.85, 1.6 into 1.6. It is coming 10 to power 20. Okay.
I think sir, like we have to do some square root. So
So this is the
from
omega
the
square, so this will be 10 to power 10, I think.
hmm.
Omega effective.
Is that answer will be around 0.3 into 0.3 gigahertz or something like
No,
that?
frequency will be 1 gigahertz.
Okay, okay. Then I am doing some mistake there. Okay, sir.
So I think this will come around. You are 0.26, right?
Yes, yes.
What you are just missing one thing. This omega p effective is equal to 2 pi f. So frequency will be omega p effective by 2 pi.
Okay, okay, okay.
So 0.26 divided by 2 into pi into 10 to power 10.
Okay, sir, got it.
this will I think come 9, then it will go around 1 gigahertz. Final answer.
Okay.
Similarly, question 7 is the plasma frequency of metamaterial is approximately. So these are both okay. So here your confusion will be solved. So we have to find the plasma frequency of metamaterial. Now you have to take Fp bulk is the plasma frequency of bulk silver take effective mass of bulk silver, that is M bulk, equal to 9.1 into 10 to power minus 31 kg. this omega p effective upon omega bulk effective, if you will find. So we have both formula, right? N effective E square by epsilon naught
ineffective.
M effective, and also we have N bulk multiply by E square, and it divide will go multiply of this one epsilon naught and M of bulk, right? So
Yeah, yeah,
this
right.
epsilon and E square will cut off. So N effective we have find 8.2.85.
5.8 to 10 to the 28.
M effective is given something 10 to 21 or some 25. 2.1 10 to minus 25 kg per meter cube, and this is given M bulk is 9.1 into 10 to minus 31 kg upon N bulk is given
5.8 into 10 to the 28.
N bulk is what?
5.8 into 10 to the
5.8, okay. 5.8 into 10 to power
28.
28. Yes, it will come around 4.61 into 10 to power minus 7. Let's see, this is 31 and this is 25, so it will be minus 6. Okay, this is 80, this is 21, so it will be around 7, and it will go to, it will come around 10 to power minus 13. ओके,
Yes, sir.
जो कि बाहर आके 10 पावर माइनस 7 बना के ये आंसर. So next question number 8 is, so there are split ring resonator are there, that is SRR be called. So this is to generate magnetic response in terahertz. Okay, so statement 1 is double SSR are preferred. Over single SSR. And S2 is double SSR suppress the fundamental electric dipole better than single SSR, thereby providing a dominant magnetic field. So which one is correct?
I think option A will be correct. Like
S1 and S1 true, S1 true, S2 false, S1 S2 false, S1 S2 true, and have explained each other कि एक दूसरे का रीजन है, that is
Yeah, if one is correct, that I can understand. Like since it is cancelling out the non-resonant inductive response. Okay. So the second one, if it is correct or not, that I am unable to get. This second one.
so see this double, see if there is one single split ring resonator, then it have some resonance, right?
Okay.
Double, and the other one is have, then that is also have some resonance frequency, and when
Yes.
they uh, interact to each other, I, when they are on the same platform, then what will happen? So you can consider like one example, one have spring resonator, okay, just a spring resonator. If you consider a spring and one mass m1 is there, okay, so that is
Mhm.
oscillating with some frequency omega 0, and the other
Okay.
mass system has some frequency omega 0, and this uh, what it is called, uh, gamma, that is the spring constant. Due to spring constant there is some loss, right?
Yes.
So if we connect both of the system with some other spring which coupled
Mhm.
to each other, right, then what will
Mhm.
happens?
The overall system will have another like a different spin constant and all. We can
Yeah,
define like
so
when.
both system has the, now will have the coupled resonator. It will
Yeah.
suppress
Right.
to each other resonances and have
Yes.
some common resonance. So one is called symmetric resonance, another is called anti-symmetric resonance. Like if
Mhm.
the both springs are stretched in the same direction,
Mhm.
that mode is called symmetric mode, right?
Yes. Yes. They will resonate and higher
Huh.
amplitude will be obtained.
And similarly, if the springs are stretched in the opposite direction,
Yeah.
then it will have the anti-symmetric mode, okay.
Yeah.
So always the symmetric mode will oscillate with the larger amplitude because they will
Mhm.
enhance each other amplitude, right?
Yes.
And the anti-symmetric mode has the lesser amplitude because this will
Yes.
suppress the frequency to each other. So I think that the second part is second statement is saying that they will suppress to each other because of the uh, coupling coefficient.
Actually, sir, what I think like S2 is false because like what is happening in case of that S2, the double acceleration fundamental.
So fundamental electric dipole better than single. See, if there will only
True, sir.
single
Yeah,
is.
yeah, this is true. The both of them are true. Right. Yes, you are right, sir.
Hmm. So mostly radiation losses are due to dipole. Okay, the higher
Yes,
order
sir.
multipoles have less radiation and they
Yes, sir.
contribute less than that. So if you have suppressed the dipole, electric dipole only, then you will suppress most of the losses from the system. Okay.
Okay.
Actually, this is the concept of BIC also, bond state in continuum. So have you understood this problem? Like if you consider the classical system, compare, then you will
Mhm.
understand better, right?
Yeah, I got that idea. What you
Yeah. So question number 9 is, the generalized Snell's law. What is generalized Snell's law? Just consider theta I equal to angle of incidence theta t is the angle in transmitted region and same Ni and Nt represents incident medium refractive index and Nt represents so and the refractive index and incident transmitted medium respectively and phi is the phase between both.
Yes, sir. I think I have got this one like is NT sin t minus uh, N1 N sorry transmission incidence and transmission. So, okay, Ni sin t minus Np sin I equal to
Ni
K
sin
K inverse at
theta I minus Nt sin theta
sin
t
theta t
is equal to
Np inverse K inverse wave vector inverse grad.
is this
It is perhaps for something like grad phi, but if the direction is x, then it is fine. Like
direction
uh, like it is written like that it is a gradient
you can
of that
consider
phase.
this type of figure.
Yeah. Okay, if this is x direction, then it is fine. Like if there is some gradient over that top surface.
So can you drive this formula?
Did I? No, no, no. I haven't tried.
So let's try to drive this. We already know the Snell law, that is sine
Yes, yes,
theta t and t is equal to ni sine theta I, right?
yes, sir.
Why this is coming? This is coming and t sine theta t, if you go to the Fermat principle, this is comes like something I sine theta I, it will equal to the delta phi. So when coming transmitted wave from one region to another region, so delta phi is equal to 0, then you can find this condition, right? So
Okay,
this was in the derivation, you find somewhere like this equation, so you have to just find the delta phi here for the two region. So we have to k into k is equal to is 2 pi by lambda multiply by n, right?
Yes.
So this is the wave vector defined.
Yeah.
So if we define ki, then it will be 2 pi by lambda into n
Dynamic.
I. Similarly,
Yes.
इंसिडेंट के लिए this is kt for transistor, it will be 2 pi by lambda into nt, right?
Yes, sir.
So this phi is defined as k dot x, right?
Okay.
So it will be so d phi over dx, if you define, it will be equal to k.
Yes, sir. Yeah, that is the dimension is matching out there.
Yeah,
Will be
or
there.
you delta phi, if you define, that will be phi t minus phi I. Okay, so this phi
Yes.
t, it will be kt into x minus ki into x. So it will be kt is equal to 2 pi by lambda will be common, and this will be nt minus ni into x.
Yes.
So this will be our delta phi, and delta n into x will be delta x, right?
Yes, sir.
For the path difference of
Yeah, the
thing,
path length, optical path
or
length.
you can say d phi over dx is equal to 2 pi by lambda into nt minus n I. So this equation will
Yes.
represent the generalized Snell's law. If you write this instead of this one, delta phi over per unit x. Okay, so you will
Okay.
put the value from here to here. Yeah, this d phi over dx, what it will represent? It will represent the rate of change of phase with respect to the position of the from one point to another point.
Yes, sir.
So the next question number 9 is there. Question number 10. So the question number 10 में there is one statement is given regarding plasmonic metasurface. So in plasmonic metasurface there is plasmonic nano antenna. So in plasmonic nano antennas, confined electromagnetic energy into extremely sub-wavelength dimension, thereby reducing the overall dimension of the metasurfaces. Okay, and statement 2 is given that plasmonic nanoantenna are lossy in the visual region and hence cannot be used for application requiring long propagation distance.
Sir, I don't have any idea. Mm.
Actually, both statements are true because this plasmon nanoantenna confines EM energy into extremely sub-wavelength, uh, thereby overall reduction of metasurfaces. Okay, क्योंकि you see this plasmonic nano antenna, जो टिप पे होते हैं ना, जो हॉट स्पॉट बोलते हैं, जिसको हम
Mhm.
प्लाज्मोनिक फ्रिक्वेंसी बोलते हैं ना, उन जैसे कोन वगैरह है, तो वो
Yes.
सारे हॉट स्पॉट्स रहते हैं. तो in hot spot the electromagnetic field is extremely confined, like if you see bow tie, you heard about bow tie, right?
Yeah, yeah.
Yeah, so energy, electromagnetic energy is extremely confined, this is true. And also the plasmonic nanoantenna are lossy because they have the k value higher than dielectrics, right? So they are lossy.
Okay, okay. Yes. Actually, I was feeling like I forgot. Like that's why it is for like for those things we have to go for some hyperbolic
Yes, yes, yes,
some
yes, right.
forgot that question. Yeah.
So question number 11 is given below are two statement regarding the plasmonic and dielectric nanosphere.
Okay.
First statement is dielectric nanosphere are not limited by the classical diffraction limit unlike the plasmonic. Not limited by classical diffraction limit unlike plasmonic. Statement 2 is the dielectric nanosphere cannot support both electric and magnetic resonance, whereas plasmonic nanosphere only support electric resonances.
Okay. Actually, I haven't gone through the last class yet, so I don't have any idea. The
Dielectric
dielectric.
support both
Mm.
electric and magnetic resonance, and plasmonic has only electric resonance. बोलो.
Sir, I haven't gone through the dielectric portion yet. The last class is still
Okay.
left, so I don't know the answer.
See, the dielectric जो nanospheres are not limited by, this is false statement because any any material has diffraction limit. Okay, that is permanent.
Okay.
Diffraction limit is lambda by 2. Whatever
Yes.
things will less than lambda by 2, diffraction will be there. Okay, so
Yes,
this
sir.
is already false. And the dielectric support both electric and magnetic resonance, this is true. And plasmonic has only electric resonance, this is also true. But why the plasmonic has only electric resonance? Why they cannot use magnetic resonance? Because this you heard about surface plasmon, right?
A little bit. I just have a little
Yeah,
idea
in
about
the
that.
previous, in the initial lecture you can see or you can read
Yes, sir.
more. So you will find that this surface plasmon has only an electric field component which is normal to the surface. Okay, so the p
Okay.
polarized light is required to satisfy the boundary condition necessary to excite SPR.
Okay.
Because for metal you know that this p polarized will be there because
Yes, sir.
there are some electromagnetic boundary condition, this E, like electric field perpendicular will be electric field perpendicular, right, in
Yeah,
angle,
yeah.
and H parallel, sorry, D parallel is equal to D parallel in. Similarly H and V are there. So these are the boundary conditions. So to satisfy this perpendicular component of the electric field, there should be on the surface some E perpendicular. So they have to satisfy this condition. Due to this, they has only electric resonances. They can excite only
Okay.
electric resonances. Okay.
Okay.
So this is due to surface plasma only. So questions are completed for the tutorial for today,
Okay, sir.
and you have some other doubt, then you can ask.
Okay, sir. Let me check.
Just I have to raise one question, if you understood it right or not. What is the physical interpretation of this negative index? We talked about negative index in the metamaterial mostly, right?
Yeah, as of now, what I have understood from the lecture, like, if I have like this negative refractive index in that case, um, the energy will flow in the opposite direction of as if the wave front is propagating. So that
Then
is why.
what will be the, then what is the uh, significance, or what is the use of that thing?
Use.
Hmm.
Okay.
Also, one question on discussion. I read one question. Uh,
Yes.
you got this mail whenever asked some question or not?
Sorry.
You got the mail when someone put one question or something, or only I get the mail regarding
No,
it?
actually, I didn't check so many things like we have an epic schedule already running
Okay,
here.
okay.
Yeah.
So n square is epsilon into mu. Okay. So
Hmm.
if you consider this n, then this will be epsilon mu plus minus, right?
Yeah.
So what is this plus minus? Plus means n is positive, then you will take n is equal to epsilon mu. This is the natural condition, or we will have the matter in nature like that. And another condition is
Yes.
n is negative, right? So
Hmm.
n is negative, then you have n is equal to minus epsilon mu, right?
Yes, sir.
So see, this is one material epsilon 1, this is epsilon 2. So ray comes here and go to this way. So this is the Snell's law satisfied, right? But if this will be epsilon greater than 0, this is mu is also greater than 0, and here epsilon 1 greater than 0 and mu 1 is also greater than 0. But what will happens for the Snell's law if epsilon 1 and epsilon 2 is less than 0, or we say epsilon less than 0 and also mu is also less than 0?
Yeah, actually, sir has done some discussion, like what I could remember, like there is some, it is some related with material gain and loss. Like, I
Yes, yes,
remember,
yes.
like,
Right. So if n is negative, it means epsilon and mu both are less than 0, and material with loss we consider, right? If material has
yeah,
loss, then negative root we will take, and if material has some gain, then we take n positive root only. Okay.
sorry, I couldn't get this point, what you said, like,
Which point you
uh,
did not get?
we take the positive root if material has gain.
Yes.
Okay, and just another question, like it will depend on the initial consideration that we have gone through, huh? If we are taking the positive root or the negative.
Which initial
Like
state?
e to the power I kx minus omega, I can take like that exponential term. Like there are two conventions, like e to
I
the power I
theta
kx.
and e to the power plus I theta, right? That you are
Yeah, yeah,
saying.
yeah,
So this theta is phase difference between mu and epsilon, right?
yeah.
Are you talking about this one?
And here also it will be like I'm just talking about like the initial consideration, the harmonic term e to the power k dot r minus omega t, or it is e to the power minus k dot r plus omega t, like this. Okay. Alternatively, we take.
I did not understand. Can you type?
Okay, it is fine. Whatever you said, I just got your point. Okay, there is no issue with that. Okay, I will verify, and if I have any confusion, I will ask you next time. Okay.
Okay, okay, okay.
Okay.
Okay. So let's stop here.
Okay. Thank you.
Okay.
Excuse me. Just I
Yeah.
have another question. Like, do you know like how many people will appear for the exam?
How
Well,
many people will appear?
appear for the exam.
I am. I can ask, but I don't have access for that to see.
Okay. Okay, fine, fine. Actually, it's like in Kolkata, in Salt Lake, many people have registered. So when I was registering for the exam, it was showing like I may have to go to Siliguri or something somewhere else for giving the exam.
Okay.
So
So,
that's why I was.
for example, I can tell you about the current is 672 learner. But how many will give the exam, that will only I will know at the time of exam only.
Okay, okay,
Hmm.
fine.
Here is only shows the total number of enrolled student.
Okay, okay.
Hmm.
Thank you very much.
Okay.
Can I leave now?
Sorry.
Can I leave now?
Yeah, yeah. I will end the call for everyone.